Hello everyone, this is Sonjoy Shuvo. Today I will discuss about resource allocation graph. So, what is resource allocation graph? Resource allocation graph is a graphical representation of the state of system. That means when we look at a resource allocation graph, we need to identify where there is a safe state or unsafe state. So there are process and resource in resource allocation graph. Usually processes are represented as an circle shape and resources are represented in a rectangle shape. There are process vertex and resource vertex in resource allocation graph. Um, in resource vertex, there are single instance resource vertex and multiple instance resource vertex. There are assignage and requested. When a resource allocating a process, then we can call it assignage. And when a process requesting to resources, then we can call it a request edge. So how we identify deadlock from resource allocation graph? If there is no cycle in resource allocation graph, then we can say that there is no deadlock. But if there is cycle, there are two possibilities for two possibilities. If the graph is single instance, then we can say that there is surely deadlock. But if there is a multi-instance resource allocation graph, we can say that there is a possibility for deadlock. Here are two examples of resource allocation graph. First one is multi-instance resource allocation graph, and second one is single instance resource allocation graph. If we want to identify assignage and request edge from this graph, we can find it very easily. First of all, R1 is allocating P2, R2 is allocating P1 and P2, and R3 is allocating P3. That means all of them are assigned. And P1 is requesting R1 and P2 is requesting R3. That means both of them are requested. If you want to solve this problem, first of all, we need to find that is there any circular weight, because circular weight is the main reasons for deadlock. P1 is requesting R2 and R2 is allocating P2. P2 is also requesting R1 and R1 is requesting R1 is allocating P1. That means we start from P1 and ended with P1, ended in P1. That means there is a circular weight. Because of there is a circular weight, we can say that there is surely a deadlock. But what if there is more process and more resources? Uh, but what if we wanted to solve with more process and more resources graph? Now, then we need to follow another process. First of all, we need to write down the assignage and request edge from this graph and put them into a matrix. Put them into a matrix from. After putting them in matrix from, R1 is allocating P1. Here, R1 is allocating P1 and R2 is allocating P2. R2 is allocating P2. And in request edge, P1 is requesting R2. Here, P1 is requesting R2 and P2 is requesting R1. Now, we write down the matrix from of the previous graph. Now, what's the available instance of this graph? Since this is a single instance graph and R1 and R2 both have a single instance, and they allocated P1, R1 is allocated P1 and R2 is allocated P2. That means there is no available instance. Can P1 get executed? Here P1 need one instance from R2, but here we see that there is no instance available for R2. That means P1 can't get executed. Can P2 get executed? P2 need one instance from R1, but R1 don't have any instance. That means P2 also can't get executed. So there is clearly a deadlock. Now, if you want to solve this graph, first of all, we need to find the assignage and request edge. R1 is allocating P2 and R1 is allocating P3. and R2 is allocating P1. That means these are assignage, and P1 is requesting R1 and P3 is requesting R2. That means these are request edge. Um, if we write down this assignage and request edge in matrix form, we find this. Now allocated what's the allocated instance of R1 and R2? R1 allocating P2 and P3, and R2 allocating only P1. That means the allocating instance are 2 and 1. And total instance was 2 and 1. We find it in previous slide. R1 has 2 instance and R2 has 1 instance. Now, what's the available instance? We know that available instance is difference of total instance and allocated instance. That means the available instance is 0 and 0 for both R1 and R2. Now, can P1 get executed? P1 need 1 instance from R1 and 0 instance from R2, but R1 don't have any instance. That means P1 can't get executed. Now, can P2 get executed? P2 need 0 instance from R1 and 0 instance from R2. And here we see that R1 and R2 has 0 instance. That means P2 can get executed. After execution of P2, it will release its allocation instance, and it will add with available instance. It means only available is 1 and 0. Can P3 get executed? P3 need 1 instance from R2 and 0 instance from R1, but we have 1 instance from R1 and 0 instance from R2. That means P3 can't get executed. Now, if P1 need to be executed, uh, now can P1 get executed? If P1 need to be executed, P1 need 1 instance from R1 and 0 instance from R2. And we have 1 instance from R1 and 0 instance from R2. That means P1 get executed. After execution of P1, P1 will release its allocation instance, and it also add with available instance. That means our new available is 1 and 1. Now, can P3 get executed? P3 need 1 instance from R2 and 0 instance from R1. And we have 1 instance from 1 instance of R2 and 1 instance of R1. That means P3 can execute it and it will release its allocation instance. Now our new available instance is 2 and 1, and our starting instance of R1 and R2 was 2 and 1. That means that means the each all of the process can get executed very with a sequence of P2, P1, and P3. Then our size sequence is P2, P1, and P3. Thank you.